Yeah, thanks again all for coming here today. So I'm going to be talking about exploring submerged volcanic islands in the South Atlantic Ocean by deep sea drilling, which is basically a kind of a very short presentation, very informal presentation, which has been designed for people that have very limited background in geosciences of an expedition that is an expedition of the International Drilling Ocean Discovery Program, or IODP, and we were the expedition 391. It's an expedition that was originally scheduled to take place between the 6th of December 2021 and the 5th of February 2022. We mostly stick to these dates, but we had unfortunately a few issues during our journey. We had problems with COVID. We were supposed to go to Cape Town, which is here, what you see in the background of that photo. And well, we went to Cape Town, but it happened more or less at the time there was the Omicron variant. So that created some issues for a few of my colleagues. Unfortunately, who couldn't join us because they couldn't get the authorization to travel. And then we had some very strict measures in hotel rooms for a week, several PCR tests, and so on and so on. And unfortunately, despite all these measures, we had a COVID outbreak on board as we were sailing towards our first drill site. So it was 3 days after leaving port, and we had at some point to cancel the operations because there were too many people ill on board. No one actually had serious problems. It was probably Omicron variant. It was very mild symptoms, but people still had to self-isolate, and then that was progressively removing the workforce until the point we had to postpone the operations. We had to go back to port, disembark ill people, and then after 2 weeks of wait, we were able to go back to the operations with a reduced drilling plan, and we successfully managed actually to drill all our key sites that are really important for our scientific objectives, despite we in the end we had limited staff and relatively limited time to do all that we wanted to do originally. So what exactly did we want to do? And that's what I'm going to talk about today. So we wanted to drill something called the Walvis Ridge hotspot to test different scientific models. One of what's called ridge hotspot interaction. Another one is called, it's related to what we call isotopic zonation. And the final one is about testing the hotspot reference frame. So if you're a bit scared about all this terminology right now, so I just want to reassure you that I'm going to explain, I hope in very simple terms, what are these different things, what is the meaning of this, and why we wanted actually to do these different tasks, or try to address these different objectives. So first of all, what is exactly a hotspot? We wanted to drill that so-called Walvis Ridge hotspot. So that Walvis Ridge is actually a ridge of submarine volcanoes that extends for about 3,000 kilometers in the South Atlantic, between Namibia and an area closer to the central part of the mid-Atlantic ridge. It's really something that is interesting in terms of geological processes and volcanic processes, because that's a surface expression of something that is taking place, something very dynamic that is taking place in the inner parts of the Earth, in the Earth's mantle. So another way to look at these Walvis ridges, or how the Earth looks like around the Walvis Ridge, is just to slice the Earth open in half, and that's what this other image here is showing on the right side. And what you see here is a relatively thin layer of essentially crust. We call also this kind of feature the lithosphere. It's a very kind of thin, rigid layer of rocks at the surface of the Earth, and then it's kind of floating on top of something that is still rock. It's not actually entirely molten magma, but it's hotter rock that tends to move around a bit quicker than what is forming the internal part of the lithosphere. And so you get mantle convection, a bit like hot water in a cooking pot. And in places, the plates are moving apart and create what is called mid-ocean ridges, like the one close to the Walvis Ridge. And along these mid-ocean ridges, you get volcanoes that are being formed because you get rising of relatively hot mantle rocks, and they're going to melt partially, and they're going to produce magmas, and these magmas are going to lead to the formation of volcanoes. So that's one way, one of the many ways, I should say, to form volcanoes on the surface of the Earth. Another way to form volcanoes is when you have within the mantle areas that are significantly hotter and tend to rise in relatively narrow conduits, in kind of pipe-like structures, and they can actually impinge upon the lower base of the crust or the lithosphere or tectonic plates. And when they do so, they can actually heat locally the material here, and they can melt the material. And this is going to, again, form some volcanoes. So here you have an example in that slide of Hawaii, where you get that hot rising mantle that is going to melt partially and form some volcanoes. So this kind of feature is called plume. And the area where you get the melting and the formation of volcanoes is called a hotspot, because supposedly the underlying mantle is hotter than the rest of the ambient mantle. And so as the tectonic plates move relatively quickly, they slide on top of the underlying mantle. That means that the volcanoes are progressively carried away from the hotspots, and they're going to age, they're going to be eroded, they're going to sink, they're just going to get colder, and they're going to sink under their own weight, and they're progressively going to be submerged. Most of these volcanoes form not hotspots, they form islands, and with time, these islands are going to be dragged away by plate tectonics, and they're going to progressively form seamounts. So that's basically what we wanted to drill. We wanted to drill a series of volcanoes that formed on top of a hotspot. And that's how it looks like in detail. That's a bathymetric model for the area that we studied. So you're here looking at about 3,000 kilometers of seamounts. Some of them are fairly elongated. Some of them are fairly small. Many of them have kind of a flat summit, which suggests that they probably formed islands that were eroded at some point of their evolution. Erosion is a way actually to remove the upper part of a volcano, and it occurs preferentially at sea level or in subaerial condition on an island because of rain, wind, wave action, etc. And so we drilled 4 different sites, which are labeled here U15, 75, 6, 7, 8. And we really wanted to drill seamounts, volcanoes that had formed, that had emplaced on top of the Atlantic plate at different times. And so the oldest ones that we've drilled, they emplaced about, we think, 80 million years ago. That's based on preliminary measurements that we did on board. And then the most recent seamounts that we drilled, they formed about 60 million years ago. So that's actually a relatively long history of the hotspot. Of course, this hotspot is still active today. It's still forming small islands around Tristan and Gough area. So we get Tristan and Gough Islands. They are modern day expressions of this hotspot. So what is interesting is if you look actually at the age progression, if you just plot the age of the seamounts along the chain versus the distance from the current location of the hotspot, what you can see is that it forms a very nice straight line. And this is because the hotspot compared to the overlying African plate or South Atlantic plate, if you like, is basically not moving much. So that means that the seamounts, if they move, if the plate is moving on top of the mantle with a relatively steady velocity, then you're going to form seamounts relatively regularly along the chain to form the chain, and these seamounts will exhibit this kind of age versus distance pattern. So and this is really a distinctive feature of many hotspot chains in the world. And so this hotspot chain here, we think also started very early during the formation of the Atlantic Ocean at the time where the Atlantic Ocean was actually very small. And most of this data was based on previous expeditions, mostly dredging expeditions. We really needed to drill the seamounts to get better material, to refine the ages and try to understand the really the detail and the complexity of this system. Another thing that's really interesting with this hotspot that formed the Walvis Ridge, it's called the Tristan Gulf hotspot because of the islands that are currently being formed, is that, well, it's only one of several hotspots that is active in the South Atlantic. You get another one forming Santa Helena Island in the north, another one forming the Bouvet Island in the south. But if you just look at all the seamounts that are formed on top of the Tristan Gulf hotspots through time, you can see that the composition of the lava is very different, and you get actually a range of compositions. And we think that these compositions are reflecting different parts of the mantle. So this is here a 3D model showing an interpretation, which is kind of speculative, but that's a reasonable hypothesis based on what we know about the evolution of the area, that you had actually different types of mantles that are underlying the hotspots, and these different types of mantles are leading to the production of different compositions in the volcanoes through time. And that's what we call isotopic zonation. So among other things, the isotopic composition of the lavas along the chain are variable, and they've changed, they've actually remained kind of consistent through time, and they have a very distinctive spatial zonation. But there are still some ambiguities about the exact distribution of which mantle source has contributed through time. As I was saying before, another interesting feature is that the Walvis Ridge started to form very early during the formation of the Atlantic Ocean. And so we think that probably the hotspot was at the time very close to the mid-Atlantic ridge. So that ridge that is the area where you get separating tectonic plates and the formation of volcanoes in the central part of the Atlantic Ocean. So here is actually a model on the left showing the age of the crust that has formed as a result of the splitting of Africa from South America through time. And you can see that, of course, the recent ocean floor is very close to the central part of the Atlantic Ocean, where you get active volcanic activity, so that mid-ocean volcanism. And if you go further away from the mid-ocean ridge, then you get progressively older rocks, and especially volcanic rocks forming the basement of the ocean floor. And actually the oldest part of the Walvis Ridge formed more or less at the same time that the Atlantic Ocean floor was also being formed. And this is what is illustrated in this tectonic reconstruction here on the right, where we think actually that the hotspot was probably formed, was very close to the ridge, and that could have led to a sort of hybrid volcanic systems where you had both volcanoes with characteristics similar to those formed at hotspots and those formed along mid-ocean ridges. So this is really important for us to understand what was the interplay between the hotspot and the mid-ocean ridge, to understand, how these volcanoes have evolved and what is the meaning of their composition. And if you look here at the situation of the Earth, reconstruction of the paleogeography of the Earth about 90 million years ago, which is relatively early in the evolution of the Atlantic Ocean, you can see that the Walvis Ridge was actually located right here. The hotspot was probably really close to the mid-ocean ridge, which is running here. So And it's important to note that this kind of reconstruction is based on a few fundamental observations from the geological record. The first one is we use the seafloor and the edge of the seafloor to reconstruct how the continents have separated through time. That works if the seafloor is still preserved today. And also we use some minerals that act a bit like compasses within the rocks. This is called magnetite. It's typical of volcanic rocks, and you can measure the paleomagnetic record in the magnetite to know where the north and south poles were located at the time of crystallization of the magma when you form the volcanic rock. So that's actually a very useful tool for us to position the continents and the oceanic crust with respect to the north and south poles through time. And these are really fundamental things to use, which were also tested during the expedition. So just to here show you another possible illustration of the evolution of the early Atlantic Ocean, I wanted to go to this nice phylogeographic reconstruction through time. Here we go. So here is basically the situation of the Atlantic today. You get, of course, Africa on one side and the Americas on the other side. And here I'm just going back in time with more or less 5 million years increments. And you can see that Africa and South America are getting increasingly closer until they're going to finally meet each other about 130, 140 million years ago. So at this time, you have actually no South Atlantic Ocean. And it's just as you start breaking apart these two continents because of plate tectonics that you start forming the oceanic crust here. And right here is where actually you have the first Walvis Ridge volcanoes being formed. So for us, it was really important to drill some of these volcanoes to see if we could find evidence that they indeed formed close to mid-ocean ridge. Also, what was important is we wanted to see how the position of the North Pole relative to the drilled volcanic rocks has changed through time. And we do this for a few reasons. First of all, it's important for us to know where the hotspots are located, because that allows us to place the tectonic plates at a given time in terms of their spatial location, and we can reconstruct how they've moved through time just by looking at the relative position of the hotspots. But also there is another interesting process, which I'm not going to explain in great detail, admittedly, which is called the true polar wonder. So sometimes actually the whole material forming the Earth move actually around the axis of rotation of the Earth. So because you get mantle zones with slightly different compositions, which we know because of, among other things, the composition of the volcanic rocks at the surface of the Earth, sometimes the whole mantle is actually moving around just to make sure that the densest rocks or materials are further away from the if you want, the axis of rotation. It's just basically a way to re-equilibrate the spinning forces, if you like, around the axis of rotation. And so there are several models about these type of processes. So the relative location of hotspots through time and how the whole mantle has moved as a whole through time as well. And they are all kind of a bit speculative and based on numerical modeling, and they are relatively well constrained, but we were lacking actually very detailed measurement of paleomagnetic data from an area around Walvis Ridge. So that was one of the main objectives of the expedition, to go there, drill lavas and try to see how the hotspot location evolved through time. Another thing that was also interesting is that for all the scientific participants, it was an opportunity for us to tackle personal research questions. So of course, we were working as a team together towards actually testing some of the big questions related to the evolution of the hotspot. Personally, I was interested in understanding the geological evolution of the seamounts and their volcanic evolution, whether they formed islands or not, what sort of rock were deposited during their formation and subsequent erosion and so on. It's the sort of work that I've done on different occasions in different places throughout my career as a researcher. And actually, about a decade ago, I was in the South Pacific drilling other volcanoes as part of an IODP expedition as well. And we found some really interesting things, drilling seamounts a few thousands of kilometers away from New Zealand, trying to reconstruct the evolution of another hotspot, which is called the Louisville hotspot. And what we found was actually not matching the models at the time of formation of oceanic islands in the Pacific, which was interesting. So this is one of my personal objectives, to do this again for the Walvis Ridge. I try to understand whether the seamounts formed islands, what was the evolution of these islands, and so on. But of course, there were other scientists on board and other research questions related, for instance, the composition of water or paleoclimatic evolution are probably going to be tested as well. So it was a lot of work being on the ship. We were slightly reduced staff, but we were still about 100 people. So it's about 20 researchers and then about 80 staff member, technical staff. So all the people managing the handling of the ship, really. You have to run it. It's a bit like a small village in the middle of nowhere. So it goes from catering to more like technical maintenance of the engines to drilling operations, etc., etc. We were using the JOIDES Resolution drilling vessel for this. And the work was never stopping unless we were in transit. But even so, we were still doing quite a few things on board, just finishing the work that was related to the recently collected cores, among other things. So it's really, there is always someone, actually half of the crew working all the time. So it's 24/7. And I was, for instance, working during the second part of the night and the first part of the day. And so, you work 13, 14 easily hours per day. But it's also very rewarding because you drill things that have never been drilled before and you never quite know what you're going to find. So there is really an exploration feeling, which is very enthusing, I guess, if you're a researcher. And so what we do is first, we collect the cores, and so they come in long tubes like these ones. This is relatively still soft material, very close to the seafloor. And this core here is going to be split in small sections, and then the sections are cut in half so that we can have a proper look at what is making actually the seamounts that we've drilled. Of course, we look at the rocks, but we do many other things. On board, there is a lot of equipment. We can, for instance, measure the density of the rocks. Something that was quite important during our expedition is there were some preliminary magnetic measurements to try to reconstruct, the location of the North Pole relative to where the volcanic rocks that we drilled that crystallized. There was some preliminary geochemical work on the rocks, but also the water that was sometimes found in the sediments. Some people were also looking at the fossils to help with the dating of the rocks. And so on and so on. These are just a few examples. There were a lot of activities. And so what we've produced by the end of the expedition are preliminary results. So here is an example of the youngest seamount that we've drilled, which was about 60 million years old. So here you have a bathymetric map. And here you have a cross section where you see the seismic profile. It's a way to image the structure of the seafloor. You have here a volcanic basement that is kind of forming the lower part of the edifice here. And the upper part is kind of layered because this is where you have some sedimentary deposits. So all the organic and dust settling through the water column through millions of years accumulating on the flank of the volcanoes. So the first thing we did was to drill through this material. In this case, we had about 200 meters of sediment accumulated during 60 million years, and we characterized the different types of sediments that we encountered. And then we reached that volcanic basement that is forming the base of the seamounts, where we had different types of lavas interbedded again with some sediment. So we can actually learn a lot about the evolution of the seamounts just by drilling and looking at the cores. And then, of course, it's going to be very important to inform subsequent research that's going to take place in the years to come by all the researchers that have taken part in the expedition. So the sedimentary cover of the seamounts that we drilled was looking a bit like this. We had different names for this. It was like, yeah, I don't know, smelly goo, ooze. There were really a range of names, and eventually when you get closer to the volcanic basement, it gets a bit more consolidated. It looks a bit more like chalk, and it's not so exciting to look at, I would say, but you have a few interesting features. For instance, here you've got this kind of rounded feature. It's actually a burrow of an animal that used to live a few million years ago on the seafloor and just made like a small burrow there. And if you zoom in and if you use a microscope, you can start seeing more interesting things. You can see all these kind of features here, which are actually old planktons. It's small fossils, microfossils. We can use them to date the age of deposition of the sediment. All the dust is also very, very tiny fossils. This is half a millimeter here. And if you zoom in, sometimes what you can, using actually here a scanning electron microscope, which we had on board, you can here see these very tiny discs, which are coprolists. It's a very small type of organism, plankton, that lives in the water column, and when it dies, it sinks, and it's going to form a sedimentary cover that can form rock like chalk. But if we were lucky, sometimes we had also some deposits of volcanic material. And what you see here on that image, that big feature here, is a pumice. So it's a volcanic fragment that was produced during a very explosive volcanic eruption, probably shallow depths, shallow water depths, or possibly on an island. Still not very clear. But these are interesting features that could be looked at for post-cruise research. Yeah, sorry, just got a small lag in my presentation. Yeah, and then we finally hit the, after going through the sedimentary cover, we finally hit the volcanic basement, and we had some lavas. Some of the lavas were very thin and forming kind of tube shapes, which we called pillow lavas. Sometimes we had very, very thick lavas, up to 20 meters in thickness, so very unusually thick lavas. And again, we were using microscopes to try to understand, in this case, magmatic processes that were related to the formation of these lavas. We had also a way to measure in situ some elements forming these lavas. So we were basically able to analyze some preliminary geochemical composition of the lavas as we were recovering them. So we learned actually quite a few interesting things already on board. Interestingly, we didn't find much evidence in the cores for the formation of oceanic islands. There were just very, very few indications, which are not very strong in my opinion, but still important. The first thing we observed in a few sediments on top of the volcanic basement and sometimes within the volcanic basement were these features, which is a type of algae. It's a red algae. We know they cannot live deeper than about 200 to 300 meters. So we know that these features that deposited in relatively shallow marine conditions. Even though we drilled here, 3 to 4 kilometers on the seafloor, so it was well, actually, we were a few hundred meters below the seafloor, and the seafloor was 3 to 4 kilometers below the sea level, so the surface of the sea, and yeah, so this material might have potentially been transported from further up from the seamount. Interestingly, we also found these very, very tiny features. So here is 0.3 millimeter. So it's the size of a sand of grain, literally. And what is interesting here is that it's rounded. And this kind of feature is normally typical of subaerial environment where you can rework material. In this case, it's a fragment of a lava. It's a fragment of a lava that's a type of lava that we did not observe at the drill site. So we think it's coming from for instance, the beach of an island that was part of the seamount at some point, and this beach has disappeared now because everything is underwater, but there is some evidence of the existence of this beach in some of the oldest sediment deposits around that seamount. So it's relatively exciting stuff. Hopefully we can find more evidence during post-cruise research to better understand the evolution of these volcanoes. Something that I'm also very interested in doing is looking at the many volcanic fragments that were found in the sediments, both in the sedimentary cover and in the volcanic basement, because I think there is potential for evidence of eruptions similar, not exactly the same, but similar to what happened this year in Tonga, where there was that huge eruptions, big eruption by a relatively shallow submarine volcano and created a lot of volcanic debris. I think we might have found similar, not exactly the same, but similar volcanic debris on the slope of some of the seamounts along the Walvis Ridge. In some cases, we had these beautiful structures in some of the cores which represent currents. I think these are actually avalanches that were created during shallow submarine explosive eruptions, and you had the material transported as avalanches downslope to form these deposits here. And that's what these deposits look like. If you look at them with a microscope, you can see all the bubbles. These are bubbles within the magma that was quenched at the contact with water. It's what we call volcanic glass, and these bubbles were made by the volcanic gases within the magma. So quite a few things to look at here, the morphology of the bubbles, but also when the material is fresh, you can analyze the composition of that quenched magma, and that tells us something about what was happening in terms of volcanic activity on the island as well. So yeah, quite a few things going on during that expedition. And yes, so there's still a lot of things to do. So if you're interested in this, I'm sure a few people from the expedition are gonna post stuff on Twitter. Perhaps I will make a small presentation in a couple of years when we have more exciting results. But yeah, all in all, it was a successful expedition. There was a lot of problems with COVID, but we still managed to collect very good materials, and yeah, we're very much looking forward to having a exciting time for post-cruise activity. So yeah, thanks all for your attention. I'm very happy to take questions if there are a few questions. As I said earlier, I'm very happy to chat to you directly, or if you want to write something in the chat, you're very welcome to do so. Yeah, I think there might be something. Where are the actual active hotspots? Yeah, they are actually, okay. First of all, I'm trying to get back to sharing my screen. It's probably better if I just keep on sharing my screen. Yeah, good question. I might have gone across a few very fundamental ideas very quickly, unfortunately, but yeah, to address your question, it would be the islands of Tristan da Cunha and Gulf Island. They are located more or less around here. Yes, more or less around here. If you really want to have a look at how they are like, you can actually go on Google Earth, and I think I have my Google Earth opened here. Let me deactivate this, and yeah, so you can zoom in, and I think you would be able to spot where you can see many of the seamounts that have some of them have been drilled. And you can zoom in, and yeah, so you can actually see some of these islands here. So that's Tristan da Cunha here. It's quite remarkable, and there is a small community living just north of the island, really in the middle of nowhere. If you zoom out here, you can see it's a very, very tiny island, which is so far out from everything. So it's really, really a long way from the nearest continent, which is, 3,000 kilometers away, straight line. But that's basically where the active hotspots are like. Are they spectacular? Well, I think they are, because these islands are just spectacular. But yeah, they're not like very, very active. These islands, if you compare them to places like Hawaii, you don't have so many eruptions, but they've definitely been active over the past few hundred to 1,000 years. And of course, so now we've got the formation of these islands around here. And as Africa is continuously separated by from the South American continent because of the spreading along the mid-Atlantic ocean ridge here, these islands are progressively going to move away from the ridge, and with time you're going to form new islands further west relative to, well, these older islands here. I think that's the two questions that I've got. Thank you for that. Yeah, I don't see any other questions. So if there is no other question, I'd like to thank you all again for coming here today. I know a lot of people are kind of tired to come to webinars, so I really appreciate that you've been here with me today. And we've got some very exciting talk coming up in a couple of weeks. We're going to have Mike Singer, so another researcher from the School of Forest and Environmental Sciences here in Cardiff University. He's going to talk about water in Africa. So we've got all the detail about the talk on our website. So it's going to happen on Wednesday in a couple of weeks. Yeah, thanks for the other comments. It was great to have you all here. Thanks all.